I'm going to look at working with tangents to solve the missing side of a right-angled triangle. In our earlier unit, you can recall that when we had a chord and it was bisected perpendicularly, that these were equal. Now we're going to look at what happens if we slide that chord up all the way out of the circle until it's no longer inside, but simply stopped and touching at exactly one point. This circle with the line on the outside has now a tangent. The blue line is the tangent line. The point right here, that singular point where it touches, is called the point of tangency. Because we were able to just slide that line outside, this angle has not changed. The point of tangency, or tangent point, is always perpendicular to the radius. Pause the video here and copy down these notes. If I were to take that same picture and simply make this blue line longer, so extend the line of tangency. I take that picture and duplicate it, flip it upside down, turn it, and line it back up. We can see that we have two radius now, and they are going to be equal. We have two 90-degree angles. We're going to add one more line. By adding a line from the center of the circle to where the two tangent points have intersected, we have now created two right-angled triangles. When we look at these two triangles, we know that the radiuses are both equal. We know that this line here, which will function as our hypotenuse, is going to be the same for both triangles. Okay. Because of that, because we have this 90-degree angle, we know that the blue lines are equal to each other. So in this picture, we have two triangles that are identical. Pause the video and copy this information down. The tangent segments are blue lines drawn from an external point to the circle are both going to be equal. Now we're going to look at how that can be used in a problem. An aircraft is at an altitude of 11 kilometers. Earth has an average radius of 6,378 kilometers. How far from the plane is the horizon? So we're solving for that length. When you look at that triangle, we can see that we are solving for the shortest side, the side we call A. We're going to start with our picture and find our triangle. The radius will be one of our legs. The hypotenuse is going to be this radius plus the height, in this case of the airplane, but in other problems it will be the height of the tower, or the height of a building, or the height of a tree. You can use a squared b squared equals c squared, or use the manipulated formula. We have the hypotenuse. We're going to take away b squared to find a squared. We know that Earth's radius is 6,378 kilometers. When we add on the additional 11 kilometers, our total hypotenuse is 6,389 kilometers. We need to square that number, and we need to subtract our short side, which is just the radius. We have two very large numbers, thank goodness for calculators, because we have squared both of these. Our next step is that we're going to subtract. Once we subtracted, we are left with 140,437 kilometers. But that number is squared. We need to take the root of both sides, the root of 140,437 and the root of a squared, to leave us with just a and 374 kilometers. This number, 374.7 kilometers, is the distance from the tangent out to the external point. Now let's look at another part of a problem. If we have this picture, we know that these lines are equal. We know that these lines are equal because of the fact that we can insert a dotted line. Okay. Once we've done that, and we know that that is a symmetrical quadrilateral, we're going to take this circle. If I take this circle and move it so that it lines up with the existing quadrilateral, takes a little bit to fuss around with it, we can see that this kind of a quadrilateral will fit within the next circle. If I remove the smaller circle, this starts to look like some of the stuff that we worked with when we worked with chords and when we worked with our inscribed and central angles. So now we have this inscribed angle, and we have two opposite angles. Okay. Opposite vertices in an inscribed quadrilateral have a sum of 180. This should be part of your notes from earlier in this unit. So how does this picture relate back to the section we're in now? Let's remove the big circle and put the little circle back in. So now, with this information, when presented with the angle of the central angle in the small circle, so where these two radii converge, we know that this external point here, these two blue dots, will have a sum of 180 degrees. We're going to use that to work on our homework today, which is due next class.